Hi. Today we'll talk about acid. So acid properties are very important when we are especially dealing with RDBMS databases, because that's what they basically promise, that the acid properties would be maintained. In this modern day NoSQL words, we have seen that the performance has been actually achieved by sort of doing relaxation on some of these properties, but I think still from a data integrity perspective, what RDBMS provide as a set of acid properties are very, very important, because they give you a very strong level of checks in terms of making sure that the data integrity remains intact. So quickly, what acid stands for? A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. Okay, so let's take an example which will give us a very clear understanding of what each property implies. Okay, so let's start with atomicity. Okay, atomicity. Okay, so let's take an example. Let's say that there is an ice cream vendor. Pardon my drawing, but let's say that he is an ice cream vendor here. Ice cream. Okay, and you want to go and buy an ice cream from him. Okay, and let's say that you have $100, which the amount of which you want to buy ice cream. I know it's a very costly ice cream, but just for an example. So now when you go and ask him for an ice cream, so what would happen is that he will give you an ice cream and will give you the money to him. Okay, so what atomicity means, that either the transaction should pass completely or should fail completely. What it means is that there should be two end conditions. One is that the ice cream wala has the $100 and you have the ice cream, or you still have the $100 for whatever reason the transaction did not succeed. Maybe you did not like the ice cream or whatever he presented to you, and the ice cream still remains with the ice cream vendor. Okay, so what atomicity means, that either it should pass completely or it should fail completely. It should not happen in any case that the ice cream wala gets both the ice cream and the money, or you get both the money and the ice cream. This should not happen. Okay, and that is what the RDBMS ensures, that whenever you are doing in the context of a transaction, because this is happening in the context of a transaction, so initiate the transaction, you give the money, he'll give back your ice cream, or he gives you ice cream and you give the money, but nowhere it should land up in this state that it fails, or and then either you have both the things or he has both the things. Okay, it has to remain in one of this state. So that is what is known as atomicity. So what it basically means, that when you say that my transaction started, so whatever operations has happened, and then when you say end of the transaction, so either each one of that operation need to succeed or everything should fail. And when we say everything should fail, so what it means is that if midway the transaction fails, it should roll out completely the states and it should bring it back to the original state. So that is what is known as atomicity. Now let's talk about consistency. Again, taking the same example, this guy has an ice cream and you have the money. Okay, so consistency also relates to what we call as referential integrity. So I'm sure if you know about, like, there are foreign key relationships between the different tables. So for example, like when you insert a data in a table and if it has a foreign referential integrity with another table, the databases will ensure that that integrity is maintained. It will not allow you to enter any other kind of data in that one. So for example, let's say that we want to create a record of transaction, and we say that in the transaction has, let's say, 4 fields. First one is the customer ID, the guy who is doing the purchase. The second one is the shopkeeper ID. Okay, and then value of transaction and the item. Okay, and let's say that it all is coming from different tables. So value would be 100 here, but item would be coming from item table. A shopkeeper ID would be coming from shopkeeper table, and customer ID would be coming from customer table. So the RDBMS will ensure that you will not be able to put the shopkeeper ID here, you will not be able to put the customer ID here. Okay, and the item ID is coming from item table. Of course, it will ensure that if you enter a key here, that item, the key of there is a row that exists in item which have this key. So again, I think you have to be very careful here. Referential integrity can only go to the point that where it will say that whether the key is there or not, and it will basically pick that from there. But if you do that mistake in your business logic, that is where RDBMS will not come into picture. But otherwise, they will ensure that key, at least whatever reference you are putting, that reference does exist in the other table. So that's what the consistency is all about. And then the third one is what we called as isolation. Okay, so what it means? What isolation means that when a transaction is going on, basically at that point of time, again, isolation has different levels. So what would happen is that, let's say, suppose that another guy as well comes, okay, and he also have $100. Okay, so what it means is that when these guys have gone into transaction, so this guy has now committed the ice cream to this guy. So this guy should not be able to commit to the ice cream to the another guy. So it should not happen that this guy takes money from both of them and actually lands up giving ice cream to only one or none. And you don't know which one will get the ice cream. So that's where this isolation comes into picture. Again, there are different levels that you can run the databases. So there is a serializable isolation. What it would mean is that when this guy comes from 100, and if this guy is already talking to him, he will not even entertain this guy. This is what also known as serializable, but that becomes very costly. Even if you look from a shopkeeper perspective, if you are going there and you are still making up your mind which ice cream to take, and until that time this guy is not letting himself to talk to anyone, it's basically he'll be lose on the business. So what he would want to do is that he would still want to interact with that one, and that's where the read committed and read dirty all come into picture. Usually that's the right level of isolation that you want to work with. So what should also happen is that in this context, basically whenever based on your isolation level, you have to maintain the integrity in the sense that when this guy has committed that ice cream to this guy, that ice cream should only take part in that transaction, and that ice cream will only be released to be given to any other customer when the transaction fails. If the transaction passes, that ice cream goes to that guy and the money comes to this guy. Okay, so that is what is all about isolation. And the durability is the last one, which is much simpler. What it means is that once the transaction happens or transaction fails, whatever is the state, so if transaction fails, the original state would continue. If the transaction passes, we will have ice cream on this side and we will have money on this side. And now this state should become durable. What it means is that whether you come like a day later or 5 days later, you should still see that as part of this transaction, the money is with this guy and the ice cream has gone to this guy. It should not happen that suddenly after some time this money again comes back to this guy from a database record perspective, and that's where the durability comes into picture. So hopefully that gives a good idea about the whole ASIC notion. And this is actually a very, very important notion to understand when you are dealing with RDBMS databases, because that ensures the data integrity of your data. And if you want to go a little further, so out of these four, you really want to look into the isolation levels. Usually databases have their own defaults, but you also want to do basically a good balance between not creating an opportunity to have a bad data, but at the same time not compromising on performance. So hopefully that was useful. Thanks.